And thank you.
Okay, that usually all flux-grown crystals are nicely faceted, like this example, and it makes a life of crystal user sometimes easier. Still, don't scroll down. This one?
No.
Ah, no.
Yeah, you need to come here. What's going on?
Oh,
I think we left, hold on. We left here. Sorry, I went to.
So first, yeah, flux method, it's the most cheap and simple one. So you simply mix your material in powder form with the flux material. So place them in a crucible, heat it up, and so at certain temperature you melt your flux material, and then your molten flux doesn't dissolve your material, and after saturation you start the spontaneous crystallization by slow cooling. And so basically that's all. So what you need for high TC cuprates, it's a very simple box furnace up to 10,000 euro. So low cost ceramic crucibles, and again low price chemicals altogether might be up to 12,000 euro, and you could start your own flux project. So it's simple, cheap, and the most universal growth method, because theoretically you could find a proper solvent for any material. The main disadvantages, so first I should mention crystal contamination by crucible material, because your flux has to dissolve your material, and at the same time it might dissolve a crucible material too. Then as we get uncontrollable spontaneous crystallization, we get many but small crystals. And the last one, how to, yes, how to detach grown crystals from solidified metal. The basic idea is very simple. It's called decanting technique. In the simplest experiment, you just take out crucible from the hot furnace and pour a liquid out on something porous. It is doable up to 1000 degrees, how it is shown on this photo. You get three standard crystals on the crucible bottom. It's indium vanadium oxide grown in our group. And this is a basic idea for any other approach, because you can do this decanting inside of a hot furnace, although it requires more complicated experimental setup. And here is a list of the most powerful, famous, and well-known fluxes like bismuth oxide, lead oxide, and several more. But the list is not complete, because we know tens and tens of different fluxes and hundreds or even thousands of materials were grown by flux. Now, I talk about crucible-free floating zone method based on optical heating. As it is crucible-free, it's the main advantage of this technique. So there is no crystal contamination by crucible material. Here you see the general view of the standard image furnace equipped by halogen lamps. So this is the control unit, and this is the main body. The most important part here is ellipsoidal mirrors, lamps, and there are two shafts, upper and lower. So you mount ceramic feed rod from your material on the upper shaft and sit on the lower. So you collect, by mirrors, you collect all emitted light and focus it in one focal point common for all mirrors. And if you place the tip of your feed rod in the focal point, you melt it, form a molten drop, touch by seed, and maintain a stable molten zone. And then you pass slowly through your feed rod upload. And so you get here crystallization of your material. And in this way, we could relatively easy grow many congruently melting compounds. Some of them are shown on these photos. These materials were grown in the group headed by Surjit Singh from India, and they give the first impression of crystal size and quality. Here you could see, we would say, very typical technical specifications for all image furnaces. So normally we could use gas pressure, oxygen or argon up to 10 bars, cooling rate, shaft rotation, and there is a whole set of halogen lamps from 150 watt up to 1.5 kilowatt. And halogen lamp produces very high temperature gradient on the edges of the hot zone, about up to 300 degrees per centimeter. So now you could see the design of the halogen lamp is the most important part. This is, it's called filament, it's heating element. And the thickness of this heating element roughly corresponds to the molten zone length. So in the first generation, it was spiraled or rounded filament, and it produces relatively large molten zone, about 10 millimeters. If we grow the same material using the modern lamps, it's single layered filament, you see the double reduction in molten zone length up to 5 millimeters. And usually shorter molten zone has always higher stability. Also, there is so-called critical molten zone length. And any molten zone that has a length above this critical value is completely unstable. So that's why we prefer shorter zones. Here you see the basic principles of the floating zone technique. Once you start the growth on ceramic sheet, you get multi-grains growth, but sooner or later, due to the effective grain selection in this technique, you get single crystal growth. And this picture illustrates how we could control the growth conditions, because in this technique we could not measure directly melt temperature, so we are based on the shape of the molten zone. So this one is more or less perfect or good shape. It means people have found nearly optimal growth conditions. Here, here, and here, the shape is better. It's not good. So again, using floating zone technique, we could grow either congruently melting or incongruently melting compounds. The last task is much more complicated due to the so-called penetration effect caused by a feed rod porosity. So, if our material melts incongruently, still we could apply this technique. So we like to grow this solid composition marked by capital S. We need molten zone of this composition marked by capital M. And if we know the corresponding phase diagram, it's quite easy task. We simply prepare a solvent rod, cut off a short disc, attach it to the feed rod and melt it. And how it is done in the real growth experiment of LSCO high TC material. So you see ceramic feed rod, growing crystal, the lamp image, and molten zone. It was obtained by melting a percentage solvent disc. And more important, this part, it is so-called penetration part. The liquid from molten zone penetrates onto the feed rod due to its porosity. And this effect even more well visible on this picture. You see this dark area is full of liquid, and really porous feed rod, it sucks liquid from a molten zone and it terminates the growth. So you have no chance to grow your material if you prepare low density feed rod. And porosity mainly depends from the sintering temperature. So if it's relatively high, above 1400 degrees, then you get high density feed rod, about 90% of density. And then the penetration effect is very weak.
Why it is better that it penetrates? Why is it better?
Because you get no solvent, you get no liquid in a molten zone. It sucks all the liquid from a molten zone.
It just breaks the process.
Yeah, exactly. Terminates the growth. And so if your material melts below 1000 degrees, then you are not able to prepare high density feed rot, and so we could not apply this technique for the growth, for example, of YBCO materials. Also, penetration length depends from a temperature gradient on the edge of the molten zone. The higher temperature gradient reduces the penetration length. So results for the flux growth of YBCO crystals, the system is the most well studied. So we know practically everything about this system, and we know the flux composition. Is it visible for people or not?
Yes.
Okay, great. So so we know the temperature range, we know the corresponding phase diagram. The main difficulty that the material solubility in this flux is very low. So we have to apply very low cooling rates, half of the degree per hour, maximum 1 degree per hour. Here, how we could separate crystals from the melt. So it's like decanted inside the hot furnace. Here it's called cold finger approach. Cold finger means it's very simple. It's just a ceramic or pipe air-cooled tube. And using this cold finger, you just localize the crystallization on the melt surface. So it's much easier to detach or to cleave crystals from the surface. And here are the typical YBCO crystals grown by flux in ceramic crucibles, either aluminum or yttrium stabilized zirconium oxide. They are quite large in AB plane, but they are relatively thin along C-axis, normally up to ½ millimeter. And the main problem in flux growth is a strong reaction between all crucible materials commonly used for flux growth with barium oxide, copper oxide melt. So, and platinum contamination kills the superconductivity in these materials. Aluminum contamination doesn't affect TC, practically doesn't affect TC, although aluminum size on copper side, and it might affect other physical properties. Zirconium doesn't enter crystal structure, although due to the very strong reaction with the melt, we are not able to prepare large size crystals. And the most inert material is barium zirconium oxide. These crucibles are commercially available on the market, although their quality and reliability is not really high. They are often cracked during the growth, and they are relatively small. So the production is still challenging for companies. So they are small, so inner diameter of this barium zirconium oxide crucible is 2.6 millimeters. It's much smaller compared with aluminum oxide, but nevertheless, people could produce really nice YBCO crystals. The most pure one with high TC, 93K. So it's still possible. So now floating zone growth of bismuth-based superconductors. It is possible to grow at least these two members of this family by flux, although the thickness along C-axis is very, very small, so it's tens of micrometers. So, and bismuth 223 could be grown by floating zone method. And nowadays, most large size and thick bismuth-based superconducting crystals are grown by floating zone. Again, the melting point of nearly all these materials are around 920, 30 degrees in air. So feed rods are very porous, but nevertheless, people, so they have developed so-called twice scanning or pre-melting technique for feed rod densification. So it's just once you get a zone between feed and seed, you pass the zone at very high speed. So, and you densify feed rod in this way. So this pre-melted rod, then you use for the growth cut. So it is done at much lower pulling rates below 1 millimeter per hour. And in this way, we could stabilize the zone and get crystals. So first undocked bismuth 201 crystals with the highest TC 7-8K. So for the growth of bismuth-based superconductors, we always use slightly off-stoichiometric feed rods. They're a little bit bismuth rich and strontium deficient. Of course, we should pre-melt this feed rod and then apply growth rate between 0.5 and 1 millimeter per hour, or even lower. Here you could see a typical S-brown ingot. In the end portion, you see very nice, very large facet. Here, the lava picture taken from this facet. And yeah, single crystals that were cleaved from this ingot. The crystallinity is quite good if you look on this X-ray Rotten curves, and you see the rise from the crystal composition. The main drawback of this system that some of these crystals are superconducting, others not. And still we don't know why, because we do not see any difference in composition or in structure. Bismuth, this is lanthan doped bismuth 201. The growth is very similar to undoped system, although lanthan substitution increases TC up to 33, 35K. And we could grow really large samples. And so with a good crystallinity that was confirmed by neutron diffraction, although still even the best crystals, they have a certain composition inhomogeneity. So, and if you look on the magnetization curves, they're relatively broad. So still it is a problem for this system. Bismuth 212. So it's the most well-studied system. So again, you have to prepare such a rod, remelt it. The best and the most thick crystals are grown using separately prepared solvent disc, but the key parameter for the successful growth is the pooling rate. It's quite low, 0.2 millimeters per hour. And only in this case, we are able to prepare such large and thick bismuth 212 crystals. If we increase pooling rate, the thickness it's below 0.2 millimeter along C-axis, and also in AB plane. The dimensions in AB plane are reduced. Again, mosaicity of the crystal is still, I would say, low. It's about 1 degree for the relatively large sample. And to see for the optimally doped crystals, it's around 91K, and we could prepare either underdoped samples by annealing in vacuum, and even overdoped, but it's still harder. It's still harder. So finally, so the most hardly grown bismuth 2223 material with the highest AC in this family. So this table shows the growth the growth conditions, and again the most important parameter is the pooling rate. So, and you see, if we use relatively high pooling rates, 0.2, 0.1 millimeter per hour, even we use bismuth 2223 composition for hydron. Nevertheless, the major phase is bismuth 212. And only when we apply extremely low pooling rates, it's around 0.05 millimeter per hour, we could stabilize the formation of bismuth 2223 crystals. And here it's a typical S-grown ingot. It was prepared at 0.06 millimeter per hour. It means 1.5 millimeter per day, and the total length is 12 centimeters. So the growth takes several months. It's very time and labor consuming process. Nevertheless, at the end, you could see relatively large facets. The lower picture taken from these facets, and here the crystals clipped from this ingot. And these two pictures, they show the effect of pooling rate on the phase purity or on the crystal purity. And so the best crystals are prepared at 0.04 millimeter per hour, but still there is a small kink around 80K. It means that still we get about 2-3% of bismuth 212 phase. We could improve the phase purity of the samples by high temperature annealing at 850 degrees in oxygen flow, by X-ray diffraction, so we get impurity-free crystals. If we look on the magnetization curves, still there is the small kink at 80K. But so the amount of bismuth 212 impurities was estimated to be around 1 weight% only. But still, we are not able to prepare impurities-free bismuth 223 samples. We always get bismuth 2212 integrals defects. Okay, now a few words about this laser-assisted floating zone setup. So it's the main part of the furnace. So you see 5 laser and infrared lasers, 5 laser diodes, infrared diodes. Here you see one of the laser beam stoppers. It's just a water-cooled metallic plate. Technical specifications are very similar to the conventional image furnace. We use O-ring sealing, so the gas pressure up to 10 bars, crystal length, growth rate, rotation. How it looks like a laser diode. So it has it requires very powerful water cooling. So there is a special separated water chiller that we need for cooling of the running lasers. The wavelength is about 1 micrometer, and the power of each laser, it's around 200 watts. Important that the laser power input is very stable with time, although there is a small, I would say, aging effect, but the time scale, it's over 1-2 years. So why laser? Okay, So each laser, it has a rectangular beam cross section. So vertical axis 4 millimeters by 8 millimeters. Of course, this is a computer simulation and how it looks in reality. So these 3 spots, they were produced by 3 laser beams. The other 2 are on the rear side and not visible. And at least so you see that these 3 spots are well vertically aligned. And the main advantage of the laser heating is a temperature gradient in a hot zone. So if we compare with halogen lamp, so the typical temperature gradient is about 300 degrees per centimeter. If we use arc lamp, okay, we get around 900, and with laser up to 2000. And here it's a real growth experiment that we performed last week with CO2 laser growth. The melting point of this material is about 1850 degrees. The zone is relatively short. For this melting point, it's just 4.6 millimeters in length. If we use halogen lamp, it's above 6 millimeters, I would say. And therefore, we could get very, very steep temperature gradient. We could measure the temperature profile along the molten zone surface by infrared pyrometer. The temperature gradient was found to be around 2000 degrees per centimeter. So it's very high value. And we believe that in this case, we will be able to grow many incongruently melting compounds that we could not grow before due to the high feed rod porosity. The most promising for the nearest future are the 123 family members like YBCO, Presidium 123 crystals. And also it might be very interesting to regrow all bismuth-based superconductors using a laser heating. Although it's much more time, labor, and labor consuming. So that's all, and thanks for your attention.
Thank you very much, Andrey. I wanted to mention that online you can also ask questions. You can type them with raise hand. We didn't try the microphone, not microphone, but okay, please question.
The question regarding melting zone. You judge the temperature of it by the shape of the melting zone.
Yes.
Is it purely empirical, like you just get experience with each material?
Exactly.
Or there is at least some there are some methods to model it, to calculate, to predict roughly?
No, empirical.
Questions?
Just go to the literature. So we are not the first group having this laser floating zone now. Did other people try to use this laser floating method to grow, for example, YBCO or
YBCO or not? YBCO.
Bisco?
Again, not, they did among all high TC group. Cuprates, it was one Japanese group, they grew barium doped. Lantan 2 couple of 4 around this.
Okay, this works, okay.
Yeah.
Also Martin, Marcus did that
Yes, yes.
That's also possible now to grow this famous 1/8, whatever.
Yes, exactly. Yes. Only this material was regrown by laser heat. Others, as I know, not. Rutinates, strontium rutinates.
This also works and it also.
Oh, it works. I mean, there is no big difference because you could grow this material by conventional image plants. There is no big difference, but they have been grown.
But Andrei said that Bisco is possible, he said, and he think, and actually for Ira it would be nice to come and start to try.
Yeah.
But as far as I understand, the main problem of ABCO is low temperature, low melting temperature.
Yes.
Which temperature is for Bisco?
Bisco 900, around 900, even lower.
But ABCO?
But YBCO 1020, 1030.
So ABCO is higher. But
High,
why
but
do
we
you
could-
expect that
but we
for
could-
Bisco is
But
higher?
we could pre-melt bismuth-based superconductors. We pre-melt ceramic feed, so we densify it. We could not apply this. It's not universal approach. We could not apply it for YBCO.
Why?
It's correct after pre-melt. It's always correct. Always correct after pre-melt.
So it's difficult to understand why, or maybe
No, because
it's just empirical experience.
it's just, yeah, empirical experience.
Just experience.
It's just,
Yeah, it's interesting for me that that it's possible to it's annealing, yeah, Oscar. It's annealing, pre-melting annealing with optical furnace that you can anneal it. I thought that you always should do it in some separate furnace.
no,
but
first you do it in a separate furnace, but then you use this feed rod for pre-melting
Yeah.
and you densify. And for this purpose, you need image furnace.
And you can control it. You just see by eyes how it became narrower. Yeah. When you go up with some heating zone, you do not have this melting region, but
No.
you just have heating zone and you go up. Or
No, normally we get a molten zone. It's like crystal growth, but we apply very high cooling rate. So you pass the molten zone at very high speed, much higher than in growth.
if it's possible. Yeah.
Yeah, if it's possible, yes.
But in principle, you can do it just to heat to some, no, not melt, but to heat
It's possible.
until
Yes. Sometimes people are doing this approach. They just see when the feed rod a little bit shrinks,
yeah.
and then, okay, now we pass. Sometimes it works for YBCO,
But for Bisco, you could.
for Bisco, yes.
Thank you. Bernd, please.
So YBCO has been studied a lot, and a lot of people say they have great, fantastic crystals. I think there have been arguments that they indeed have good crystals.
Except praseodymium 1, 2, 3.
I presume this does work, I agree. And YBCO still the floating zone portion.
Nobody did it before.
Yeah, can it might lead to larger crystals. That would be-
Yes, of course,
Big
much
thing.
larger and much thicker along surfaces. Yes, of course.
Yeah, actually, we discussed about large enough for neutron experiments. And he remembers that in Keimer's group, they did it sometime long ago, but as far as I remember, and this is actually that Nature Physics paper, when we compare this for YBCO, but we would be much happier to compare Arcus and neutron for this, of course, not for YBCO. More questions? Then Sam shows the speaker again. And